Start. Hello, AP Calc. This is Mr. Ford. We're doing the notes for 5.2.1, the product rule. And before we get too far into this, it's probably a good idea for us to flip all the way to the end and see the product rule before we even start. You'll see it all the way, the math notes at the end. And if I was teaching a different style of AP Calc class, I would certainly start with this thing right there. I would start by showing you the product rule. It's a very simple rule, actually. As it turns out, it's pretty easy to memorize, and it's really easy to use. But if you're looking for the derivative of some product, f of x times g of x, you have to follow this simple little pattern. F prime times the original g plus original f times g prime. Basically, the derivative of the first times the original second plus the original first times the derivative of the second. And the nice thing about the product rule, it's pretty forgiving because the order doesn't really matter on any of those. Since the only operators are multiplying and adding, you can really just not worry about the order so much. The quotient rule, you do have to remember order for, so we'll deal with mnemonics for that. But we are going to be doing a proof of this together in just a moment. However, you could memorize this right now and go crazy. But let's actually flip through to the next problem. We're actually going to, this is on my practice page with my notes on it. Let's go to my blank page. So let's go, before we do that, let's consider a case of a derivative that we currently cannot do, which is j of x equals x times the sine of x. Presently, we have no way of finding that derivative. It's now that when we have the product rule, we will be able to. But that's just one example of many derivatives that we currently cannot do. We've been limited on how many actual AP Calc questions I can show you, because typically, after you teach the power rule, you teach product rule right after, and that has not been the case this year. So, but I think we're in a much better position because we have a much better understanding of things. So let's look at 548. I'm going to guide you through this proof. It's actually pretty straightforward, and I had never seen anything like this until a couple days ago when I looked at it for the first time. And I was like, that's actually a really cool way of explaining the product rule. I could just show it to you, but this is a good way of thinking about it. Typically, we'll go for some sort of area model. So we've got Hannah. You guys remember Hannah, our friend? It's actually important because all the limits in this problem are Hannah's limits, the ones that start with f of x plus h minus f of x. But we'll deal with that in a minute. When she's thinking of f of x times g of x, she immediately thinks of this rectangle. And you'll notice that f of x times g of x is this main section down here. That's the area of this rectangle. This is a helpful way to think about a derivative because it really gets to the root of what a derivative actually is. Question A is that j of x is the area of the rectangle. So what does j prime of x represent? And j prime of x represents, because it's a derivative, it's the rate at which the rectangle's area is changing. Which is what we measure in calculus with derivatives. We talk about the rate at which things are changing, j prime. And essentially, to do this, what we've done is taken the original f of x and the original g of x, and we've just added a tiny nudge onto both of them, which we're calling h in this diagram. Sometimes we call that dx or something like that, but h is a very small number, and that's why all of the limits in this problem have limit as h approaches 0, because we want to think about if we increase g of x and f of x by some little tiny nudge, how does the area of that rectangle change? And that's exactly what we're going to investigate visually with this. So to determine the value of j prime, she sets up this problem as follows. Yeah, look at that ridiculous limit right there. It's actually not too tough if you think about it. Oh, yeah, hi, Peter. It's the limit as h approaches 0 of this thing, f of x plus h times g of x plus h, which if you're looking at those dimensions, that's the area of the whole rectangle. F of x plus h is that green length down below, and g of x plus h is this red length on the side. And from that, we're going to subtract, I've got it highlighted in yellow, so I might as well stay with yellow. We're going to subtract f of x times g of x, which is the area of the original rectangle. And we're going to see what happens when we make h go to 0. Essentially, when we make that little tiny nudge that we increase those dimensions by, we're going to make that go to 0. But so far, all you need to understand is that this is the limit as h approaches 0 of the big rectangle minus the original yellow rectangle, which helps explain what's going on in this next step here, because she sketches a rectangle in which the shaded area represents the numerator, and she's got this statement right here, which is that if you look at the top of that fraction, that is, in other words, f of x plus h times g of x plus h, the big rectangle, minus the original yellow area, it equals the area of A plus B plus C, which is basically what's left over. A plus B plus C. So far, all we've got right now is that the big rectangle minus the original yellow space equals those extra sections that were added on there. And what we want to do is we want to measure what the size of those new sections is as h approaches 0, as we start increasing the area just a tiny little bit. So you'll notice in part C what she's done is she's replaced the top of the original fraction, this original expression right there, she's replaced it with its equivalent, the area of A plus B plus C. So the question, what did she do? All she did was replace one thing with an equivalent thing. Remember, this is a walkthrough of a proof. It's not meant for you to completely understand this, but if you can kind of vibe with what's happening, it's pretty powerful. I did show you what the product rule is 5 minutes ago, but that's not as cool as seeing why it plays out the way it does. Now we're going to use a lot of limit rules to show what's going to happen here with this area of A plus area B plus area C thing. Let's jump into part D here. Now what she's decided to do, she's actually going to break this up into 3 separate limits, because you can do that. She's going to think about the limit as h approaches 0 of the area of A over h, plus the limit as h approaches 0 of the area of B over h, plus the limit as h approaches 0 of the area of C over h. So we're going to investigate all 3 of those chunks on their own and see how it shakes out. Let's start with area A. So again, if you zoom in on this statement for a minute, what she's doing is we're finding the limit as h approaches 0 of area A over h. And the area of A can be expressed by this multiplier, f of x, the original f of x, times g of x plus h minus g of x. Let's look at A for a minute. Let's just draw it off to the side for a minute. Just draw a quick little picture of what area A looks like. It's just a rectangle, and its left and right dimension is just the original f of x. And its height, the h, can be found by taking g of x plus h and subtracting the original g of x. So that's where that expression comes from. Again, if I were to take this entire distance here and subtract off g of x, we'd be left with just the h that's left there. So that's how we're finding the length and the height of that expression. And again, we're finding the limit as h approaches 0 of that area there. This is just for rectangle A. Now the cool thing is that you can, again, separate this into 2 separate limits, which is exactly what she's done. You've got the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x over h. That's a lot of gobbledygook, but if you take a look at it for a minute, underneath it, let's just think about this. First of all, h does not affect that chunk at all. H isn't anywhere in there. So the limit as h approaches 0 of f of x is just f of x. And the second part of it you might affectionately recognize as the formal definition of a derivative. We can call that g prime of x. That's exactly what that is. It's the limit as h approaches 0 of g of x plus h minus g of x over h. This is just g prime of x. That takes care of the first section. Now, if you flipped ahead and looked at the product rule, you might recognize where this pattern is going. Let's look at part B, area B. It's very similar, very similar. This time area B looks more up and downy than left and righty, but it's the same kind of idea. The height of the rectangle in part B is g of x, the original g of x. And the width you can find by taking the f of x plus h and subtracting the original f of x. Again, if you look at the picture, there's your rectangle for B right there. The height of it is g of x, and the width is f of x plus h minus f of x. That's what's left over. So again, we're going to look at the limit as h approaches 0 of that area, of that rectangle, which you see, again, right here. Limit as h approaches 0 of g of x times f of x plus h minus f of x. And again, if you're looking for patterns, which is always a good thing to do in your math class, you'll see the exact same thing is happening. That's just g of x. H doesn't affect it because h isn't a part of it. So this is just g of x. And again, this you'll recognize, again, affectionately, that's just the formal definition of the derivative of f of x, f prime. What's really fun is this section C, the area for the rectangle C, which is kind of the top corner there. Now, a much easier way to say the proof that's about to happen is that if h is going to 0, and that means that this side is already really small, and this side is also really small, if you multiply a really small thing by a really small thing, the product of that is just basically nothing. You can ignore it. Yeah, that's exactly what's going to happen here. If you look at the proof, again, the length and width of rectangle C can be represented by f of x plus h minus f of x and g of x plus h minus g of x. And if you separate that into two separate ideas, you got, right here, you got f prime, like it was from the previous part. And then you got this guy over here, which actually is really easy to think about because h is a part of this. If you make h equal to 0 in this function, you just get g of x minus g of x, which is 0. And so it turns out it doesn't matter what f prime of x is because it's being multiplied by 0, so that whole last little rectangle C is worth nothing. And so for part G, here is the product rule, which if you've got nothing else out of that little walkthrough of that proof, here is the product rule, which we should write maybe somewhere right here. This is part G. The product rule works like this. J prime of x, the area, ends up being, if you put these parts together, you got the original f of x times the derivative of g plus the original g of x times the derivative of f. And that is the product rule, my friends. So if you got nothing out of this, there it is. And we're going to practice it a couple times before we leave. That's it. It's actually really easy to work with. The best way to handle product rule problems is, first of all, to recognize what two things are being multiplied together so you can identify what f of x and g of x are, pull them off to the side, figure out their derivatives, and then you just put it together in this little formula. Let's take a look at an example. Let's try h. This is a problem that we totally can do without using the product rule. I would never recommend that you use the product rule for this problem. It's much easier and faster to do by expanding it and then using the power rule, but let's just practice our new skill for now. We're going to call f of 4x minus 1 is going to be called f of x, and 3x plus 1 is called g of x. The fun thing about product rule is that it doesn't matter which one you call which because you're multiplying them together, so the order doesn't matter. None of the orders matter in product rule. It's much more forgiving than the quotient rule. I like to make a little chart like this. This is how I kind of learned how to do this in high school and college, and so it's kind of the way I pass on to you guys. I'll put my f of x and my g of x right next to each other, and I just kind of build a little imaginary table like this. So underneath this, I'll keep track of what f prime is, which in this case is just the number 4, and g prime over here, again, just the number 3. Couple quick product rules there, or power rules. And then when you go to use your product rule, it helps when you're first learning a formula to write it out again. J prime of x is going to equal the original f times g prime plus the original g times f prime. I've seen a lot of people use u and v for this too. Yeah. I don't like using u and v because I think they're too similar of letters. I have to make sure to make my u's extra round and my v's extra pointy, but u prime and v prime, I've seen people do that. That helps too. Doesn't matter. It's the same idea. So all we got to do now is plug it all back in together. So the original f was 4x minus 1 times g prime, which was 3, plus the original g, which was 3x plus 1, times the f prime, which was 4. There's kind of a crisscross pattern. The reason why I like using the table is because it's kind of a crisscross pattern to it. You multiply the original f times g prime and the original g times f prime, and you add them together. Now you can simplify this, obviously. It's 12x minus 3 plus 12x plus 4, and it ends up being 24x plus 1. Hey, cool. Which you could confirm right now if you wanted to expand it all the way out. If you were to expand this, this would be 12x squared plus 4x minus 3x, so it's plus 1x minus 1. And again, the power rule can confirm you get the same derivative, so it doesn't really matter. This is a bad example to start off with because I would never recommend you use the product rule for this. Much faster to use the expand it, use the power rule. But if you go to the next page, let's try looking at that example that we saw a minute ago that we could not do. So let's do some new derivatives. A whole new world of options is available to you now that you have the product rule in your tool chest. Let's differentiate x times the sine of x. This is a really common one. Again, I think it really helps. I'll do some more off to the side here because it helps to organize your thoughts. Let's say that our original f of x is just x, and so f prime is just equal to 1. And g of x is going to be the cosine of x, or sorry, sine of x. I was thinking ahead too fast. And so g prime of x is the cosine of x, just like that. Helps to organize your work. I'd like to make a little table like that because it helps to remember which ones will get multiplied by which other ones. And so the derivative, what did they say y equals? They did y equals, so we'll do y prime. So the derivative would be x cosine of x plus sine of x. Sine of x times 1. Da-da-da-da-da. Hooray. And all we're doing here is multiplying the parts together. X times the cosine of x is the f times g prime. And sine n times f prime, g of x times f prime of x is the sine times 1. Right there, and you add them together. And again, the nice thing about the product rule is that the order does not matter, so you do not need to memorize which one goes first or second or whatever, because you're just multiplying and adding. So sine of x plus x cosine x is also valid. And all the same rules apply. If you were to graph this, you would then see all the slopes that are happening back in x times sine of x. You'd see all the same things. You could find maximums, minimums by setting it equal to 0. You could take the derivative again if you wanted to, which would be insane. You'd have to do another product rule for x times cosine x. You could find concavity, all that stuff. Let's try... I don't know if question C is worth us doing. Is it worth us doing? Yeah, let's try C. Let's get another rep. I don't like these sneaky ones. I don't like that they throw sneaky ones at us right away. Plus, all of these have better ways to do them later on anyway. So let's try C. We'll do one more. Let's first of all set it up. Let's call f of x. I think, is it x plus 2 or x minus 2? Uh-oh. Hang on. Let's go to the book. I don't like...
It's a minus.
Is it a minus? Do you think so?
Mine has a very faint minus.
Let's go with it. I trust you. We'll go with it. Not that it matters too much anyway. Look at that magnetic attraction.
Oh, I see. Oh, yeah, it's definitely a minus.
Definitely a minus? Okay, good. Confirmed. Confirmed.
I'm like, do you see it? Like, you won't be able to see it.
Okay, so let's call f of x will be x minus 2 squared.
It's right. There.
I can scroll even wild imagination.
No, look.
Okay.
It exists.
Take your word for it.
You should.
Now again, this one you could expand out, but as soon as you start seeing exponents that are like to the third power or fourth power, then it gets to be like, I don't want to expand x plus 5 to the third power. You could do that. I don't want to do that. It ends up taking way more time.
I haven't opened it yet. Frosted cranberry. I don't know, I got it in my stocking. I forgot to bring it out to my car, so that's what I was doing, but I forgot again,
So like all product rule problems, the problem starts with you identifying that you need to use the product rule in the first place, and then kind of mapping out your original f of x and g of x, and then your derivatives down below. There is a little bit of simplification that we could do with these, but I wouldn't recommend going too far. In fact, I want to leave, I see f of x and I see g prime. They have those quadratic binomials in there. They're not too tough to expand out, but you know, we're going to start multiplying these all together and then adding them, and it could get to be a real headache if we try to do it the simplest way possible. So the only thing I'm going to do is with f prime, I'm going to simplify that to be 2x minus 4. But that's the only one that I think is worth doing. In general, you've heard this advice from me a lot this year, is if you don't have to expand it or simplify it, then don't. Leave it exactly the way it is. Let a computer deal with it, or a calculator deal with it. So for our product rule, we're going to do f times g prime, and we're going to do g times f prime. We're going to do our best to just keep that as straight as we possibly can. So y prime, or you know what, let's mix it up. How about dy dx? They all mean the same thing. So let's do f times g prime. Let's keep it simple as we can. X minus 2 squared times 3 times x plus 5 squared. That 3 in the middle is going to bother me. If I was more particular, I'd make sure the 3 goes to the front as a coefficient, but I don't care. It's not worth worrying about. Plus, let's do x plus 5 to the 3rd power. That's our original g of x, times, maybe in parentheses, 2x minus 4. Something like that. Nope. And again, walk away. Don't do anything else. Okay, I'm going to move that 3 in front. It's going to bother me if I don't.
Oh.
3 times x minus 5. I know, I have to. It's worth it. And I'll put 2x minus 4 goes in front also because it goes in order. Yeah, depending on I don't know if you have a future math teacher in front of you or what kind of old crotchety or foreign person they're going to be. So it depends. Depends on. I only speak for the truth. At least what my experience was at CMU. So.
I hope you're my last math.
Usually you'll have some sort. My hope for you is if you have 2 paths, whether you're going to keep going or whether you're not. And if you're not, you're going to take a competency class that will be an absolute non-issue for you. That would be my goal on Trail A.
Like algebra 2?
Yeah, maybe like that. Maybe pre-calc, maybe something like that. Most degrees are going to require that you take something. They're going to require that you take. No, you'll be amazed. You'll be amazed how much you retain, and you'll be like, oh, that's nothing.
Yeah, right. I just printed out the unit circle because I didn't know how to use it.
Oh no. Unit circle's so much fun though too.
Shocking.
All right, so here it is. In case you got nothing else out of this, there is your product rule. Know it, love it, get it tattooed in your arm, memorize it now.
Bet, I'll do that.
The hardest part about the product rule is honestly identifying when you need to use it.
Is that a tattoo?
Yeah.
Tattoo, it's the unicircle.
Same.
Yeah.
Unit circle's been on my short list. I've been thinking about getting a math tattoo. F of x is 1 over x is one that I wanted to.
Do it.
The formal definition of a derivative. I met a guy who had the limit definition derivative on his calf at a calculus thing.
Where would you get it?
It was, to be fair, this was at a convention for AP calculus teachers. So.
And you still got it.
I
Yeah.
love Taylor Swift, but I wouldn't get her.
I would
Yeah.
get a picture of
I
James.
saw like there was a guy got a tattoo
They don't know
or
where it's from.
there was some engineering
I haven't finished my answer guide for the homework, but the homework is this section here. Everything except for the last question, not 558. I got interrupted on my prep. I got about halfway through 555, so that's where I am right now. Tomorrow I'm out. I left instructions for my dad's subbing, so
No way.
yeah. I got a circuit training for you guys. I haven't copied yet, but it's all maximums, minimums. There's a couple functions on it that you don't technically know how to find the derivative of yet, so I did that for you.
Everything
I
for it.
told you what the derivative is.
Wait, doing all of them?
Are we doing all the homework or skipping one?
Not the last question.
Wait, they wrote
Just
it.
get the last question. I forget which one it is.
I thought it was like no.
558.
Okay, maybe not.
The first one, this is really practicing homework. It's like the first 5 problems are just like just do much. Integrals and derivatives.
Like I'll have my backpack to school, and I'll just end up like driving 6 more.
Oh, chain rule is next. Yes.
I'm not driving. I'm sitting.
I've made the drive before.
It's how you take the derivative of a composite function. Have you guys noticed on the homework there's been a bunch of the composite functions are coming back? There was that one, Jeff showed me the one where it's like x and then an arrow, f of x, then an arrow, and then g of x. Yeah, that's the next thing. Chain rule is necessary, but it's also one of the ones that people bounce off of quite a bit. So it takes a little bit of pracky to get the hang of. What's next? Algebra 1? What? Oh, thanks for reminding me.
That was much fun. We're bouncing.